This machine looks like a twisted sculpture from a sci-fi movie, but it just shook the entire energy industry. What's happening right now here? It's the cover of the Chrysler that's being built here that you see up top there. In a quiet German town, scientists have done the unthinkable, keeping superheated plasma stable for 8 minutes straight. So, it's a well-behaved plasma. And the difference to before is that we would have to sit and watch this for 8 minutes. That's longer than any fusion reactor of its kind, and they're not even at full power yet achieved fusion ignition, and that is creating more energy from fusion reactions. While the world waited for France's massive-eyed project, Germany quietly raced ahead with something different. A bizarre-looking machine called the Wendelstein 7X. It could bring us clean, limitless energy. No meltdowns, no carbon, just raw power. And now the world is finally paying attention. This is one of the most impressive scientific feats of the 21st century. Wendelstein 7X. Tucked away in the small coastal town of Griswold, Germany, sits a machine that could change everything. It's called the Wendelstein 7X. And it doesn't look like any reactor you've seen before. Shaped like a metallic pretzel from another dimension, this reactor isn't about splitting atoms, it's about fusing them. After nearly 2 decades of construction, this experimental device came to life. And in 2022, it stunned the scientific community by holding plasma for 8 minutes. That's not just a record, it's a revolution. So, we do want to find out if we've made a plasma. Most people expected breakthroughs from big projects like France's ITER. But while they were still building, Germany had already switched on a different kind of machine, a Stellar. Where others saw complexity, German engineers saw potential. The W7X was their bet. An expensive, risky, high-precision gamble. And now it's paying off. This isn't some flashy startup or overhyped lab demo. It's real and it's running. And though the public barely noticed, those in the energy world certainly did. Because if this strange machine works, the energy game may never be the same. Nuclear fusion versus fish energy isn't new, but the kind we've used for decades. Fish comes with baggage. It splits atoms, generates power, but also leaves behind dangerous waste. Long-lived, hard to store, risky if things go wrong. Think Chernobyl. Think Fukushima. Fusion flips the script. Instead of splitting atoms, it fuses them just like the sun. The result, immense energy, no carbon emissions, no meltdown risk, and the waste, minimal and short-lived. Fusion uses hydrogen isotopes, common light, and found in water. When fused, they produce helium, a harmless gas. No toxic leftovers, no weapons material. Safety is built into the physics. If something goes wrong, the reaction stops. It's like trying to keep a candle lit in a hurricane. One gust and it's gone. That's why fusion has been called the holy grail of energy. But for 60 years, progress was painfully slow. The joke? Fusion is always 30 years away. Until now. Germany's W7X isn't just chasing fusion, it's catching it. And unlike traditional reactors, it might just be the first design that's truly ready to deliver clean power without the risks that haunted nuclear for decades. The race for fusion isn't a one-nation sprint. It's a global marathon filled with giants. The United States has the National Ignition Facility and SPARS. China boasts its East Torque. The UK runs JET and MAST. South Korea is busy with K-Star. And then there's it, a 20 billion behemoth rising in southern France. Each of these projects hopes to crack the code of fusion. Most follow the same blueprint, a donut-shaped machine called a tokamak. It's the design everyone trusts. Safe, predictable, familiar. Then came Germany. Instead of following the herd, they built something else, something stranger, something harder. A stellarator. While tokamaks are symmetrical and easier to model, they have a flaw. They need an electric current running through the plasma to stay stable. That current is tricky. It wobbles. It fails. Stellarators skip the current. They twist their magnetic fields into complex shapes that can in theory hold plasma steady forever. but they're a nightmare to build. Most countries gave up. Too complicated, too expensive, too ambitious. Not Germany. They poured in the time, the money, the precision, and now the Wendelstein 7X is proving that the underdog may have had the better plan all along. Choosing the Stellarator wasn't just bold, it was risky. For decades, the world walked away from this design. Too complex, too unpredictable, too expensive. But Germany leaned in. While others refined the tokamak, German physicists and engineers went deep into the math and deeper into the unknown. For a long time, scientists have believed nuclear fusion to be the greenest answer. They spent over 1 million hours designing the Wendelstein 7X, ran supercomput simulations, tweaked magnetic fields into bizarre, beautiful forms, built machinery so precise it could make a watchmaker nervous. The cost, over $1 billion. The reward, a shot at the future. Most experts didn't believe it would work. Even fusion insiders called it a long shot, but Germany didn't care about the odds. They cared about the potential. And now that gamble is starting to pay off. The W7X isn't just working, it's excelling. It's running plasma more stably for longer durations than many tokaaks, and it's doing it without the constant current that need. For the first time in decades, the fusion community is rethinking everything. Maybe the hard path was the right one. Germany bet on the complicated, on the twisted, on the strange, and suddenly the world is realizing they might have been right. Building the Wendelstein 7X wasn't just a scientific challenge. It was an engineering miracle. Imagine crafting a machine the size of a house, but with the precision of a Swiss watch. That's what German engineers faced. At the heart of the reactor are 50 superconducting coils. Each one has a unique twisted shape impossible to bend into place. So, they had to be cast, carved, and machined from scratch. Creating many stars inside reactors like this is one of the greatest technological challenges humanity has ever faced. The tolerance less than 1 millimeter. One wrong move and the magnetic field wouldn't hold. The plasma would escape. The fusion would fail. To prevent that, engineers built custom robots, specialized milling machines, and a one-of-a-kind assembly facility. Every piece was scanned, measured, rechecked. Then came the cryogenics. Fusion plasma reaches 20 million degrees. The magnets must stay at -270. That's colder than deep space. Just meters apart, the W7X handles a temperature difference greater than the gap between an ice cube and the sun. To make it possible, they built one of Europe's largest liquid helium systems. Kilometers of piping flowing through a machine with no room for error. And when they flipped the switch, the magnetic field matched the model perfectly. A fraction of a % off would have ruined it. But they nailed it. That's not luck. That's precision. That's German engineering at its peak. Most fusion experiments celebrate when they hold plasma for a few seconds. That's how fragile the process is. A flicker of instability and it all collapses. But in late 2022, something extraordinary happened. The Wendelstein 7X held plasma steady, not for seconds, but for 8 minutes. That moment changed everything. 8 minutes of high-performance plasma. Temperatures hitting 20 million degrees C, strong confinement, high density, and all without melting down. This wasn't just a new record. It was a message. Fusion no longer had to be a burst. It could be a sustained flame. And here's the kicker. The reactor wasn't even running at full power. It was using a temporary cooling system, a placeholder. The real system is still on the way. Once upgrades are complete, scientists expect longer runs. If we achieve everything to put all the elements together to make fusion happen, then we have an abundant clean CO2 neutral climate neutral energy source. More heat, more control. The triple product, a fusion metric combining temperature, density, and confinement time was approaching the threshold needed for net energy. No other stellarator had ever come close. With this run, Germany didn't just break a record. They broke a belief that fusion had to be short, unstable, and unscalable. Now the world is watching because this wasn't a lucky shot. It was a preview. And the next chapter, it could be even hotter. Fusion has always been a dream. Clean power, no emissions, no disasters, just pure star-like energy. But for decades, it felt out of reach. The science was tricky. The machines were delicate. The costs were crushing. Then came this 8-minute plasma and everything changed. This wasn't just a record. It was proof. Proof that the Stellarator, the oddball of fusion designs, could actually deliver. While tokamaks struggled with current-induced instabilities, the W7X stayed calm. No wobble, no crash, just sustained heat. That's the holy grail. Steady-state fusion. Not bursts, not flashes, but energy you can count on for power grids, for cities, for the future. And Germany's machine isn't theoretical. It's already running, already learning. It showed that complex doesn't mean impossible. That strange shapes can hold real power. And suddenly, the fusion roadmap looks shorter, clearer, because this machine didn't just trap plasma. It freed the industry from decades of doubt.